All right, I think we're ready for the concert next week, don't you? Why not? You sound great.
Because you have to practice too.
But I've been with you the whole time and I've been following along and I know how it goes.
But you have to practice for yourself.
Oh. Welcome. I'm Dr. Courtney and I have practiced this problem, so let's see how it goes. We're talking about two climbers sliding down icy slopes of different angles, but they're coupled together by a rope, and we're asked to find the acceleration. Now, since we have forces and accelerations involved, we expect that we will be applying Newton's second law. Now, since we have two climbers, that is two separate bodies. So we will be applying Newton's second law to each climber, and they have masses m1 and m2. They're on different parts of this mountain, so they're sliding down different slopes of theta 1 and theta 2 respectively. And we are given the task of finding the acceleration. And we're told, so we want to note that they are coupled together. The two climbers are coupled by a rope. This is the primary task. We're asked another question which we will address as we develop the problem and evaluate it. As usual, we will begin developing the problem by drawing a picture, then making a point-by-point plan for evaluating it. So we have a scenario something like this. Climber 1, which we'll indicate by this square, which I'll label 1, and climber 2 will be labeled square number 2. And they are on different slopes. Climber 1 is at an angle of 11 degrees. Climber 2 is at an angle of 38 degrees. The mass of climber 1 is equal to 73 kilograms. The mass of climber 2 is equal to 60 kilograms. And they are coupled together by a rope. So we will include that in our sketch here. And we assume that the rope maintains tension at all times, that it doesn't go slack. We'll call that tension T. And so coupled together, these climbers are accelerating down the icy mountain. As we make a plan for evaluating this, we want to always start by checking our units. And if any given values are not in MKS units, we will convert them. Secondly, we will make two free body diagrams this time, one for each body. Each of the free body diagrams will be labeled with all the forces acting on that particular climber and a coordinate system that applies to each climber. Then we want to recall Newton's second law in equation form. Then we want to express Newton's second law in the direction of sliding down the mountain, which, as you'll see, we will call the x direction, again, for each climber. So we were going to develop two sets of equations, one for climber 1, one for climber 2. Then we potentially have a number of unknowns and a number of equations that we will need to work with to isolate the variable that we're interested in, which is the acceleration down the mountain. So the next step, we're going to explicitly consider or decide how to eliminate unknown quantities and solve for the acceleration. So I'm making a plan to think about it. Since I don't have the equations in front of me right now, I can't really think about it ahead of time, but we need to make a note that we will be considering that explicitly. Then, once we do that, we want to solve for acceleration. And express that answer to the correct number of significant figures. Then there's a part B in which we're asked, well, what if climber 1 puts an ice pick in the ice so that they stop their acceleration down the hill? Then we're dealing with a static situation. How much force does the ice axe have to support? And so to do that, we're talking about summing the forces in the x direction. And that's how much force the ice axe will have to support. And then reporting that to the correct number of significant figures as well. Okay, we're ready to evaluate. As we check our units, we are given angles and degrees, masses both in kilograms, so we are good to go and do not need to convert units in this particular problem. We're going to take a few minutes to develop free body diagrams carefully because they will be very useful to us when it comes time to write out our equations. First of all, for climber 1, we will concentrate the mass as a point mass, and I actually want a little more room because we're going to draw some specific information on these diagrams. Climber 1 has a weight, which we'll call Fg sub 1, and that's equal to the mass of climber 1 times gravitational acceleration. Now, what other forces are acting on climber 1? Climber 1 is on a slope of 11 degrees. I'm going to start by drawing that as a dashed line here. I'm drawing that because there is a normal force acting back on the climber because they're on a slope, and that normal force is perpendicular to the surface that the climber is on. What else? Well, there's a rope coupling these two climbers. That rope is acting in the x direction, or what we will call the x direction in a moment, down the hill toward the other climber. Okay. So this is the tension force that is also acting on the climber. These are all the forces acting on climber 1. Now we need to choose a coordinate system. Since we're interested in the acceleration down the hill, and we're interested in minimizing the number of vector components we have to compute, we will designate the downhill direction as our x direction. Then perpendicular to that, which also happens to be parallel to the normal force, will be our y direction. By choosing the coordinate system this way, we only have to resolve the weight vector into components. So let's see how we will do that. The weight vector then will have a component of Fg1 sub y, that is the y direction that we've designated. However, it acts opposite to the direction of the normal force. And we have a component in the x direction, Fg1x. Now, how much is that? We do have to resolve that component. Since the slope that this climber is on is 11 degrees, the angle here is also 11 degrees, and so the x component, Fg1x, is equal to Fg1 times the sine of theta 1. And that's equal to m1 times g times the sine of theta 1. Now we are ready to work on our second free body diagram. Climber 2, similarly to climber 1 of course, has a weight force acting on the climber. However, this weight force is now Fg2, which is the mass of the second climber times gravitational acceleration. This climber is on a different slope, a steeper slope of 35 degrees, excuse me. There's a normal force acting on this climber also, so that's going to be normal force 2. Now the tension in the rope on climber 2 is acting in the opposite direction as it was on climber 1. And so we have that tension acting this way. Now notice I did not label the tension T1 and T2. Because the rope is common between the climbers, the tension in the rope is the same in each free body diagram. Okay, and we will designate the downhill direction for this climber as the x direction, which makes the y direction also parallel to the normal force. We will resolve weight components for climber 2 as well. So we have an x component, Fg2x, and a y component, Fg2y. This angle is also going to be 35 degrees, and so we can resolve the weight component for climber 2, Fg2x is equal to the weight force for climber 2 times the sine of the angle for climber 2, which is equal to the mass of the second climber times gravitational acceleration times the sine of theta 2. So we've taken longer than we often have had to developing these free body diagrams, but this entails a lot of the work that will allow us then to move straightforwardly through the rest of the problem. So now we are going to express Newton's second law, which is that the net force is equal to the mass times the acceleration vector. We've established that we are interested in the acceleration in the x direction, so that's what we will focus on for the rest of the problem. So for climber 1, that means that F net x1 equals the mass of climber 1 times the acceleration, and F net x2 is equal to the mass of climber 2 times the acceleration. Now, similarly to the way that we used a single designation of t for the tension because it was common between the two climbers, the acceleration is also common between the two climbers because they are coupled together. So we can then, that was our step 4. Now we will develop these equations by substituting values. So for climber 1, the forces acting in the x direction are the tension force and the component of the weight in the x direction. So we have Fg1x plus the tension force equals m1a. We can substitute our expression for the x component of the weight force, m1g sine of theta 1 plus the tension equals the mass of the first climber times the acceleration. Now for the second climber, let's just make a little division here so we realize that we're working with climber 1 and climber 2. Similarly, in the x direction, we have the x component of the weight force for climber 2. This time the tension is acting in the opposite direction. So if for climber 1, if this is plus t, for climber 2 it is minus t. That's equal to the mass of the second climber times the acceleration. Substituting for the x component, we have the mass of the second climber times g times the sine of the second angle minus t equals m2 times the acceleration. Now we have two equations with a lot of symbols in them. Let's take a moment to consider which symbols we know values for and which we don't. We know the masses, we know gravitational acceleration, we know the angles. We do not know the tension, we do not know the acceleration. Therefore, we have two unknowns, which are the tension and the acceleration. Fortunately, we have two equations, and if we have two equations and two unknowns, we can find a solution. That brings us to step number 5. We need to decide how to eliminate unknown quantities and solve for the acceleration. So our choices are substitution or elimination. We'll discuss those for a moment and how we can decide. If we choose the approach of substitution, that means we choose one of these equations and solve it for either the tension or acceleration, and then substitute into the second equation and solve for the remaining unknown. Elimination involves adding a multiple of one equation to the entire other equation in such a way that one of the variables is eliminated. Then you go on to solve for the remaining unknown variable. Either way is mathematically acceptable and can be correctly executed in this problem. However, as I look at these equations, I have a plus t, plus a tension force, and minus tension force. So to me, that says that using the elimination method will be the most straightforward approach. So we will do that. Let's rewrite these equations so that you can see. So we have m1g sine theta 1 plus the tension equals the mass of the first climber times the acceleration. And our second equation we'll write directly underneath. The mass of the second climber times gravitational acceleration, sine of the second angle, in this case minus the tension force, is equal to the mass of the second climber times acceleration. So we can add these equations together term by term, and you see then that the tension force is eliminated in this process. So we end up with a longer expression Now again, this equation has many symbols in it. Let's take a moment and remind ourselves that the only unknown now is the acceleration. So our next steps will be geared toward isolating that acceleration and computing its value. Let's rewrite this expression by factoring out a common term to make our computations easier in a few moments. So we can factor out gravitational acceleration from the left-hand side. And we can factor out acceleration on the right-hand side, and then it's left as a multiplication of the sum of the masses of the climbers. Now to isolate A, we will divide both sides by the sum of the masses. So on the right-hand side, the sum of the masses then cancels and we're left with an expression for acceleration. At this point, we can substitute values and compute what the acceleration will be. So that is 9.8 meters per second squared, gravitational acceleration. The first mass was 73 kilograms times the sine of 11 degrees plus the second mass, 60 kilograms, times the sine of the second slope, which is 38 degrees, all over the sum of the masses, which is 73 kilograms plus 60 kilograms. And through careful computation, we find that that acceleration comes out to be, let me give you the numerator and the denominator as intermediate steps here. So we'll have 473.767 kilograms times meters per second squared in the numerator, and 133 kilograms in the denominator, which gives us an acceleration of 3.5622 meters per second squared. Reporting that to the correct number of significant figures, which brings us back to step 7. So we just completed step 6 here. So the acceleration is, we will use 2 significant figures because our given values have 2 significant figures. So this rounds to 3.6 meters per second squared. Now, in part B of this problem, we are asked, what if one of the climbers puts an ice axe, if climber 1 puts an ice axe into the side of the mountain, stops the slide, then in a static situation, how much force has to be supported by the ice pick? Well, that's just going to be the sum of the forces in the x direction. The slope itself supports the components in the y direction. So the sum of the components in the x direction is already shown here in the numerator of our expression for the acceleration. This is the x components of the weight forces for each climber. So that we already computed as 473.767 kilograms times meters per second squared. So reporting that answer to two significant digits, we have that the ice axe would have to support 470. Now what about our units? Kilograms times meters per second squared is the definition of the unit of Newton, named after Isaac Newton. So we have 470 newtons as our answer to the second part of this question. Before we conclude, let's assess our answer to see whether it makes sense. First of all, we always want to look back at our units. We save substituting specific values until we have as simple a symbolic representation as we can get, which in this case didn't look so simple. We substitute meters per second squared for acceleration. We have kilograms for the masses. Kilograms is divided out, so we are left with, see, kilograms and kilograms divide out, we are left with meters per second squared for acceleration, which is what we would expect, and we already discussed the unit of newtons for the force that the ice axe would have to exert. Now, so the units check out. What about the magnitude of our answer? Well, we expect the acceleration to be greater than 0, so 0. But what about an upper bound for the acceleration? Well, they're not falling straight down, are they? So we expect the acceleration to be somewhat less than gravitational acceleration. And similarly, what about the force that the ice axe has to support? It's going to be smaller than the total weight of the two climbers because the slope itself is supporting some component of their weight. So we also expect that the force in the axe is going to be greater than 0, but less than acceleration times the sum of their masses. And that figure is something like 1,000. So we expect it to be less than 1,000 newtons. So we see that our answers are within the lower and upper boundaries that we can establish for both the acceleration and the force needed by the ice axe to keep them from sliding down further. So by considering units and the magnitude of our answer, by conducting our calculations carefully, we can have confidence that our solution is the correct one.